everyone! Today we are going to talk about structures, about the basic concepts to be able to do exercises, and about beams. And we will explain what's the relationship that's between the shearing stress, the bending moment, and the charge that we apply on a beam. So, let's go! Okay, first we are going to talk about the basic concepts about structures. So, first, let's start with the supports. We have two types of supports. This one, when we have this drawing, we will have to draw a vertical force and a horizontal force. But instead, if we have the simple support drawn like this, we only have a vertical force. Okay, now we are going to talk about clamping. That in Spanish it's called Empotramiento. Okay, these are when we have something and it's attached to a wall or to the floor or wherever. So in this case we have a vertical force, horizontal force, but we also have a moment that makes this able to stand still and not to rotate or whatever. Okay, another concept is if we have here a rod, if the forces acting on it are like this, we have to say that this rod is working to traction. But if we have this rod and the forces are in this direction, the rod is working to compression. And now we have an important concept. If we have an articulate rod, so for example, a rod that is like this rod, it's articulated here and here. If this rod has no mass and this rod, there are any forces acting on it, no forces, external forces, the reaction forces that of this rod are on the direction of the rod. So here, as you know, the reaction can be this way, or whatever. But if the rod has no mass and there are any external forces acting on it, the reaction goes on always in the direction of the rod. Okay, now we are going to talk about beams, vigas in Spanish. So we have here a beam, we are applying a charge on it. So what can happen with this beam when we are applying a force, a charge or even on it? Okay, they appear shearing forces. That this is when the beam can break like this. Sure. The bending moment is when, for example, we are applying, okay, in this case it could be in the other direction. If we are applying the charge like this, it would bend, and if the charge is very high, it would end up breaking like this. And the normal forces, if like the charge is applied perpendicularly to the beam, equals 0. Okay, now we are going to explain the relation that happens among the shearing stress, the bending moment, and the charge that we apply. So here we have a beam, and let's say this is the charge we have on it, Q of X, whatever, it has not to be uniform or anything. So First, we are going to explain what's the sign convention to these forces that we have to use. So, if we cut this beam like this, if we take this part of the beam, the forces must be in this direction. The shearing first B, that this is called B, has to be downwards. The bending moment has to be in this direction. Okay, and the normal force that will, in these cases, will always be 0 in this direction. Okay, here we'll have also these forces, H and B. But if we take this part of the rod, the direction of these forces reverses. So B, the shearing force, the shearing stress would be in this direction. The moment would be in this direction, and the normal force would be in this direction. Okay, and here the support force, that's vertical. Okay, now we'll take a differential part of this beam, like this piece, that it's the X. So let's make here it bigger. Okay, this is a beam. Okay, this is the X, and our system of reference is in this way. So this is X positive and Y positive in this direction. So the shearing stress here in this part, as it's like we are taking the left side of the beam, of the broken beam, B is downwards, and the moment is in this direction, M. In this other side, we have to invert its sense, so it will be upwards, and the moment in this direction. Okay, and the normal force in this case will be like this, and in this case would be like this. But is it okay? No, because here we are moving a differential quantity. So here it's in B, because if we have here B, here the shearing stress will be B plus differential B, that's the quantity that the change in the shearing stress between this part and this part of the differential piece we have taken. So here the same isn't B, it's M plus the M, and here it's N plus the N. Okay, and we don't have to forget that here we have our distribute charts Q of X. Okay, now we will plantate the equilibrium equations. So what we will plantate the equilibrium? The forces on the vertical direction must sum up to 0. So let's write it. The sum of all the forces on the y direction equals 0. The forces on all the forces on the horizontal direction must sum up to 0. And all the Turks, with respect to a point, we'll take this point as reference, for example O. The sum of all the Turks with respect to our point O must equal 0. Okay, so this will be 1, this will be 2, and this will be 3. Okay, so 1. Forces on y direction must equal 0. So what will we have here? B positive, B minus B plus dB plus Q of X times the X, that is the weight of this portion of beam that we have written. Q of X equals 0. The second, in the X direction, what do we have in the X direction? Okay, M plus the N positive minus n equals 0. Okay, and now the torques. As these are free moments, despite we have chosen this point as our reference taking the torques, we have always to write this one, whatever they are. So here, the third, this, we have taken the positive direction of torques, so as this turns like this, m plus the m will be positive, m plus the m. Okay, and now this is in this direction, so it's negative, minus m. Now with respect to this point, it's b makes a torque b times dx negative, minus b times dx, and the weight of this portion of v it applies on the center, so this is dx over 2, and the weight is always vertical. From this point it makes a positive torque, so plus q of x times dx over 2, and this all equals 0. Sorry, here was dx missing in the previous equation, because the total charge, that is the force of the weight of this piece of beam, equals the charge distribution times the distance, so sorry about that. So what do we have here? This cancels with this cancels with this cancels with this, and as this is a second order differential, it can be neglected. So from here, what do we obtain? First, this is the first, this is the second, and this is the third. So from the first equation, we obtain that q of x equals minus dv over dx. From the second equation, we obtain that dm equals 0, and from the third equation, we obtain that b equals dm over dx. So what does it mean? That the charge distribution equals the negative derivative of the shearing stress with respect to the length, that dn equals 0, that means that n is constant, and that we also obtain that the shearing stress is the derivative of the bending moment with respect to the length. I am Vanessa. Thank you for watching. See you in the next video. Bye!